Baby Shawties, welcome back. All right, time for some happy, joy, fun time. So what we're going to talk about in section 4 now is we're going to get some sass going on here. We're actually going to talk about solving equations that contain exponents, or where the thing we are solving for, our variable, our unknown, is going to be found in the exponent. This is what's called an exponential equation. Exponential equation is when we have our variable as an exponent. So for example, like we've been seeing so far this chapter, let's say I give you 2 to the x. So the thing that I'm solving for is in the exponent as compared to things we solved before, like 2x, okay? So we learned some things on how to solve equations, but really what we did when we solved equations, we were always solving linear equations, okay? We're now going to be solving exponential equations. And in our last section, we just talked about the difference between the two. So our goal for today is we're going to talk about how to solve exponential equations. So we do have to learn something new, and then we're going to make use of some of the things we've learned before about solving equations. So we're going to make use of what's called the property of equality for exponential equations. It's very similar to how we deal with equations in general. Anytime you use an equal sign, you are essentially saying that the left side and the right side are identical to each other, right? So if we had just a regular linear equation that we were solving, we could use some addition, subtraction, multiplication, division properties that if I did something to one side, I'd need to do it to the other in order for things to remain equal. Now, we're going to make use of this fact that when things are equal, that means the left side and the right side have to be the same, okay? So what the property of equality for exponential functions is going to say is that if I have the same base, so notice here the base is going to be my number like 2, that's the base here, that if I have the same base, that means my exponents must also be the same, or must also be equal. So if I'm saying, okay, 2 to some power has to equal 2 to the 5th, well, here's what I know. If my bases are the same, then I can say right away that x equals 5. So essentially, if my bases are the same, I can set my exponents equal to each other in order to understand what my x needs to be. And when knowing x is 5, essentially what I'm saying is that 2 to the 5th power is equal to 2 to the 5th power. And no duh, right? The left side and the right side have to be identical in order for them to be equal. So we're going to make use of this property to solve exponential equations. Key thing when solving this is we need to make sure that we have the same base for both the left and the right side of the equation. Okay, so in order to use that property of equality, the bases need to be the same. So notice this first example, we have 3 to the x plus 1 equals 3 to the 5th. Our goal is to figure out what x needs to be. Some of you, again, might be able to kind of just look at this equation and solve it. What does x need to be in order for the left side and right side to be identical? But the way we're going to do this is first recognize that my bases are both 3. Okay, so I have the base here is 3, and the base there is 3. All right, so what we're going to do, if the bases are the same, I'm going to take my exponents, x plus 1 and 5, and I'm going to write an equation, x plus 1 equals 5. So essentially what I'm doing is just looking at the exponents, I'm essentially writing a linear equation from this exponential equation because this is stuff we know how to solve. If I want to solve this for x, what I would have to do is subtract 1 from both sides and get x equals 4. All right? Now, if I were to plug that in, if I plug 4 in where x goes, I would have 3 to the 4 plus 1, which is 3 to the 5th. And because it's an equal sign, I know that 3 to the 5th is identical to 3 to the 5th. Okay, so plugging that value of x in, we're just looking at the exponents, but we see that the left side and right side are identical to each other. So that's the first thing I'm looking for is, do we have the same base? Okay, so the next example, I have a base of 6 and a base of 6, so we're good to go there. So what I'm going to do is set my exponents equal to each other. So first of all, we do see 2x minus 3 on the right side. So I know for my equation here, it's going to be equals 2x minus 3. Now I kind of skipped over it because what are we going to have for the exponent here for this 6? All right, so notice the exponent is not shown there. If the exponent is not shown, be careful there. A lot of people are going to want to think it's 0. Okay, but 6 to the 0 power will actually give us 1. So the number that actually is there is going to be 6 to the 1st power. Think of that as that we have 1/6 there. So what I'm going to do is set 1 on the left side. So if the exponent's not shown, understand that it's always going to be the number 1. And now my goal is to solve this linear equation. All right, so this one we just have multiple steps here. So I would start off first by adding 3 to both sides and getting 4. Okay, and then that would be equal to 2x. And then lastly, I'm going to divide both sides by 2. And I would get x equals 2. And again, to plug that in, if I were to take 2 and plug it in where x goes, I would have 6 to the first on the left side. And on the right side, I have 6 to the 2 times 2 minus 3. Well, 2 times 2 is 4. And then 4 minus 3 is 1. So notice that my exponent on the left side is 1. My exponent as a result on the right side would also be 1. So plugging that in, notice how it makes the left and the right side identical in that equation. All right, last example here for example 1. 10 to the 3x equals 10 to the 2x plus 3. Fantastic. Right here we see the same bases. I have my exponent as 3x. Here I have 2x plus 3, so I'm going to take my 2 exponents and set them equal to each other. So 3x equals 2x plus 3. Okay, the only thing, as you can see here, I started off with just a 1-step equation, a 2-step equation. Now I got a multiple-step equation where I got variables on both sides. So anytime we see that, we do want to gather our variables on the same side. So again, we're just setting this up as a linear equation. We're going to solve it as a linear equation. So here to gather my x's, I would subtract 2x from the left side and from the right side, bring it to the left side. 3x minus 2x would give me 1x, and then that's going to equal 3. So then lastly, to get rid of that 1, not that this is necessary, but if I were to divide both sides by 1, I would get 3. So I know here that x needs to equal 3. And again, just to show you by plugging it back in, if I do 10 to the 3 times 3, that would give me 10 to the 9th. And on the right side, I'd have 10 to the 2 times 3 plus 3, which would also give me 10 to the 9th. So notice by plugging in that value of 3, we have the same base of 10, and it results in the same exponent of 9. And that is, again, what it means for things to be equal. We want the left side to be identical to the right side. All right, we're going to throw some wicked sassy now, babes. What happens when I don't have the same base? Ruh-roh. So when we don't have the same base, what we're going to simply do is just try and set the equation up such that they do have the same base. So I might have to modify some things, change some things, so that I can use that property of equality for exponential equations. So first example, we have 5x equals 125. So I want to know what value of x would I plug in there to get 125. Now, sure, I can, plug in some numbers like 1, 2, 3, 4, 5, 6 and see which one gives me 125. That's Gucci. But what we're going to do now is I want to show you how to set this up using that property of equality for exponential equations. So to do that, I'm going to take, notice here on my left side, I have my base of 5, my exponent of x. I'm going to take the right side, which is not written in exponential form, and I'm going to take that number 125, and I'm going to try and write it in exponential form. Okay, now to do that, my left side, I have a base of 5. So what I'm going to think about is, can I rewrite 125 as a base of 5? And the answer is yes. 5, think about this, 5 to the first power would just be 5. 5 to the second power is 25. 5 to the third power would give me 125. So I can rewrite that as 5 to the third power. And now by setting my bases are the same, by taking my exponents and setting them equal to each other, I would get x equals 3, and voila, problem solved. Now again, this is probably a problem you could have solved without doing this change of base, I guess, if you will. But this way we can do it is by making the bases the same. Because that's what it means for them to be equals. We're trying to make the left side and right side look identical to each other. The second example here, notice that we have both problems are both left side and right side have a base, but the base is not the same. I have a base of 4 on the left side and a base of 2 on the right side. So what I'm going to do is I'm going to rewrite this, okay? Now, the best way to do this is we're going to take the larger number. In this case, I'm going to take the 4, and I'm going to try and rewrite that number 4 using a base of 2. So what I want to think about, I'll write this in parentheses, is 2 to what power would give me 4? So 2 to the first would give me 2. 2 to the second power would give me 4. So I know it's 2 to the second power. So I'm going to change that number 4 to a base of 2. But notice that that 4 already had an exponent of x. I'm going to place that x on the outside. And that's going to be equal to then 2 to the x minus 3. So notice how I changed that 4 to 2 to the second power. 2 to the second power is still 4. It just looks a little bit different, okay? Same thing, but different. Now what we're going to do is we want to try and solve this, but here I have parentheses, right? It's 2 to the second power, that's 4, but we have that x. Okay, so what we want to do in order to get rid of the parentheses, we're going to use a property called the power of a power. Okay, power of power means that I have here a power of 2 and a power of x. So when I have a power to a power, what I'm going to do is simply multiply those two things. So 2 times x would simply become 2x. So I can rewrite that as 2 to the 2x power, and that would equal 2 to the x minus 3. So kind of a longer process, but what I did is I started off with 4 to the x, and now I rewrote it as a base of 2. Again, my exponent had to change, but why I did that is now I have 2 as the base on my left side and 2 as the base on my right side. So when solving then, what I'm going to do is take my two exponents, 2x and x minus 3, and I can set them equal to each other. So I ignore the base. Once the bases are the same, I want to know what do my exponents have to be in order for them to be the same. So again, this kind of looks like the third example from example 1. And then I have a multi-step equation. So here I want to gather my x's. So say I want to subtract x to both sides. Remember, there's always a 1 in front. So 2x minus 1x would give me 1x. And that's going to equal -3. And then again, I can divide by 1, which is not really necessary. But if I just want to take some extra time and do that, I would get -3. And again, if that goes back to the very beginning, if I were to take -3 and plug this in up here, what I'm going to get is the same result on both sides. So what I had to do here is had to change the base. So I went from 4 to a base of 2. All right, this last example is going to blow your minds here. I have 9 to the x plus 2 equals 27 to the x. So I notice the bases are not the same. I have a base of 9 on the left side and a base of 27 on the right side. So what I want to do is I want to get them to be the same base. But here's the only pickle in this problem, folks, is that if I go to the bigger number 27, and I want to say change that to a base of 9, well, that won't work because 9 to the first power is 9, 9 to the second power is 81, so there's no way that I can change 27 to a base of 9. But here's what I want to see if you guys can recognize. That 9 and 27 do have kind of a common base, and that is the number 3, okay? I know that 3 to the first power is 3, but 3 to the second power is 9, and 3 to the third power is 27. Whoa, so what I can do in this problem is instead of changing one of the bases, I can change both. I'm going to change this 9 to 3 to the second power, and again, I'm going to keep its exponent already, x plus 2, and I'm going to change 27 to 3 to the third power, and again, keep its exponent that's already there as x. Now, just like I did in the previous example, I'm going to use that power of a power rule. What I'm going to do is I'm going to take my exponent of 2 and multiply it by x plus 2, and I'm going to do the same thing with 3 and x on the other side. Now, when I do it on this side, notice I'm multiplying one thing by two things, so I'm going to have to distribute. So I'd get 3 to the 2x plus 4 equals 3 to the 3x. Notice now that I've changed them both to a base of 3, but now I have my exponents of 2x plus 4 and 3x. So once I get to that point, then I can rewrite my equation looking at strictly the exponents. So I'm using the exponents to write myself a linear equation. And what I can then do is solve. Again, gather my variables on one side, so I'll subtract that 2x. I got 4 equals then 1x, and I don't have to do this next step, but I'll just do it because I know some of you love it, but I'll divide by 1 to get x equals 4. So this one's a little bit sassy because I had to change both bases. So if the bases are not the same, this is where you're going to get the challenge. When bases are not the same, we got to make them the same before we do anything else. All right, the last two examples here are going to just throw you guys for a loop here, but what we're going to do now is how do we solve these exponential equations when, one, we don't have the same base, and when one of our bases is between 0 and 1. So you're going to see that base as a fraction, okay? So what we're going to do is we're going to try and use some tricks and trades of things we learned about before, hopefully with exponents. So real quick, just know that when I, let's say, see a fraction, like in this first one I have 1/2, that all fractions can be rewritten with an exponent. And that what happens is that, think of my base here as being the number 2, my denominator, okay? So what this means is that instead of, like a normal exponent would mean multiplication, I'm multiplying by a number multiple times. When I see a fraction, I'm dividing by a number multiple times. So we can actually rewrite a fraction using a positive base, or sorry, I should say a whole number base. So I can write 1/2 using a base of 2, but what ends up happening is I'm going to take my exponent. Now, think of 2 as 2 to the first. I would take my exponent and make it negative. So 1/2 is the same thing as 2 to the -4th. I could pick any fraction. So for example, I could say 1/15th, and I could say that that would be 15 to the -1st. Okay, so I can do that with any sort of fraction, and I can rewrite it using negative exponents. Now, it's going to help us because what we're going to do is try and solve these using that change of base. So 1/2 x, for example, I can rewrite this as 2 to the -1st, and then again, it already has an exponent of x, equals 4. Now again, when solving this, I want to try and make my bases the same. So what I want to do is try and write 4 using a base of 2, and I know that 2 to the 2nd power would give me 4. So notice I had to change both the base on the left and the right side, but I also had to use negative exponents on the left side. So when simplifying this, again, I would have to then combine my two exponents using that power of a power rule. So -1 times x would be 2 to the -1x power, and that's going to equal 2 to the 2nd power. So then I'm going to work with my exponents, -1x and 2, and I would write myself a linear equation from that exponential equation, -1x equals 2. So then lastly, dividing by -1, I would get x equals -2 as my answer. And again, -2, if I were to plug that into the original equation where x goes, if you did 1/2 to the -2nd power, you would get 4, okay? So it ends up giving you the answer as a result. But again, what we're going to do is change the base, but also change that fraction using a negative exponent. All right, let's do the same thing for this next one. I have 4 to the x plus 1 equals 1/64. So notice I have the fraction on the right side. So I'm going to keep the 4 to the x plus 1. Whoopsie daisy, silly me. 4 to the x plus 1 there. And then 1/64, I'm going to write that as 64 to the -1st power. Okay? Okay, now I want to make sure the bases are the same. So I have 4 to the x plus 1, 64 to the -1st. So what I want to do is change the base of 64. So I'm going to rewrite that. So I want to know, can I rewrite that using a base of 4? Which I can. 4 to the 1st power is 4. 4 to the 2nd power is 16. 4 to the 3rd power would give me 64. Then I would have -1 on the outside. Again, I'm going to keep that exponent still there. And on the left side, I would have 4 to the x plus 1. Okay, then I would still need to simplify those two. So again, like I've done before, I'm going to multiply 3 and -1. So I would have 4 to the x plus 1 equals 4 to the -3rd power. And in the last step here, I'm going to take my left side and my right side, my exponents, and I'm going to write a linear equation from them. So x plus 1 equals -3. And then my goal is to solve for x. So if I were to just subtract 1 here from both sides, I would get x equals -4. Careful with the negatives there. All right, now just to show you again, plugging -4 in, if you were to take and plug -4 in all the way up here, what you would get is 4 to the -4 plus 1, which would be the same thing as 4 to the -3rd, which if you plugged it into a calculator would give you 1/64. So again, we can take our idea of our changing our base to make them equal. We can use some interesting facts about negative exponents to try and solve these equations. So notice, a little bit more complicated than a linear equation, but we are making use of our ideas of exponents and our knowledge of exponents, as well as our knowledge of linear equations to try and solve these, okay? So just remember, as you do this, it's all about making sure the base is the same and using some things like negative exponents or that change of base in order to solve these exponential equations. A little bit more challenging section here, so make sure you jot down any questions. Reach out to myself or Ms. Casper if you have any questions, comments, concerns, queries, or quagmires. Talk to you guys later. Good luck on the practice. Peace out.